So, a very good morning. Welcome to the summary session. So, today we will just discuss very rapidly. We will just go through all the topics, whatever we have studied, whatever we have discussed in these 12 weeks. Uh, so these are all the topics that we discussed in this course. So, we'll just go through them very fast. We will just try to recall. Okay, so we'll just try to recall whatever we have studied. Let me just check. Yeah. So I hope I am audible. Yeah. So as I was saying, I am just going to uh, yeah, I'm just going to uh, just go through all the discussion that we had in the past 12 weeks. Uh, so we won't go much into the details. We won't solve any problems. Just that our memories get refreshed once. Okay, just to end this course, just to summarize everything, we will go through all the um, discuss all the presentations of this discussion sessions once very fast. Okay, so yeah, I hope the screen is visible also.
Yes, sir. Sir,
Okay,
visible.
okay, okay. Screen is visible. So let us start. So in the first week, what we had done is that we just introduced the topic of geosynthetics. Before that, what we did, what we just solved some basic problems from basic soil mechanics, and after that, we introduced the topic of geosynthetics. So what are geosynthetics basically? So I had given some pictures and uh, I asked you to identify what these are. So first one was geosynthetics. This one is geogrid. Then this third one is geomembrane that we discussed yesterday. Then this one is actually GCL, geosynthetic clay liners, that also we discussed yesterday. Then this one is actually geocomposite. So here we have geonet sandwiched between two layers of geotextile. So now we know it very well that why actually this thing is done. So the sandwich geonet will actually serve as a drain. Okay, serve the purpose of drainage, and the geotextile layer which is placed at the top and bottom and actually serve as a filter. Then we had also solved some problems regarding geocell and also regarding these PVDs. Right. Okay, just a second. Yeah, yeah. So just we discussed all the type of geosynthetics. So basically there are natural geosynthetics and artificial geosynthetics. So natural geosynthetics, they are very important for sustainability reasons, right? So natural geosynthetics, they are mostly made up of coir and jute. And why are natural geosynthetics important? They are important from the point of view of sustainability. Okay, sustainability and also environmental impact. And then we have artificial geosynthetics. Those are made up of polymers or metals. So what are the some basic functions? So one function can be separation function, filtration, reinforcement, erosion control, drainage. Okay, then barrier. We have also barrier function. All these things actually we had discussed, right? So what are the main types of geosynthetics? Geotextile, geogrid, geonet, geomembrane, PVD, GCL, this one, geocell and geocomposite. Okay, so geotextile also there are many types: woven, non-woven, geogrid, uniaxial, biaxial, right? So we discussed all those things. Okay, so the first lecture was just the basic introduction. We discussed all the basic types of geosynthetics. Okay, and we also discussed about these polymers, how geosynthetics are actually manufactured. That also we discussed in very brief. So these are the functions BDE, FPRS, barrier, drainage, erosion control, filtration, and all those things. Huh? Okay. So in the second week, what we did was we recapitulated whatever our basic soil mechanics concepts regarding the triaxial test. Okay. So what is triaxial test? How it is done? How much height to depth ratio we should have? Then what is deviatrix test? What are P and Q? How to get the normal stress on any plane, shear stress on any plane? What is the critical angle of failure? All these things we had discussed. Okay. Okay. From any test, how can we get this failure envelope? And from where failure envelope, we can actually get this cohesion and the friction angle of any soil. So this is the basic equation as we all know from the mode column failure theory. Then we saw some test results. So here you can see. So for unreinforced soil, the strength of the unreinforced soil is quite low, and as the strength increases, as the soil is reinforced with increasing number of layers, so one layer, two layers, three layers, five layers. Okay, so reinforcing the layers with a number of reinforcement such as geogrid, geotextile, anything. So with that, what happens? The strength of the soil is actually increasing. So that is shown here. So it is for one confining pressure and this for one more confining pressure. Okay, so from these test results, what we can do, we can plot the PQ graph. From the PQ graph we can get the phi value. Okay, the phi value of the soil. So this is very important. We discussed there are two explanations for the increasing strength of reinforced soil. Okay, for the increasing strength of reinforced soil, there were two main reasons. Right. So the first reason was this uh, increase in friction angle. Okay, this can be explained by the increase in friction angle. Okay, total friction angle, and the second reason can be explained with the concept of apparent cohesion. Okay. Then what are the things that matter? Uh, Spacing of reinforcement, spacing, we already designed the spacing, we solved some problems where we designed the spacing. Okay, the spacing depends upon the strength of the reinforcement, the stiffness of the reinforcement, also the interaction between the soil and the reinforcement. These are frictional properties between the reinforcement and the soil. Then yeah, so then here you can see we have written the expression for the this rupture force. So twice 2 into sigma v, that is the twice of the 2 into sigma v times length into width times tan delta. So sigma v means the vertical stress times the length into the width times tan delta, that is the friction that comes from the friction ratio, and twice because upper and lower. Okay, so this place is geosynthetic, so upper is also contact with soil, lower portion is also contact with soil. So 2 into this one. So if tensile strength is greater than this force rupture, this RP force, then the failure will be with pull out. And if the tensile strength is less than this RP, then the failure will be with rupture. Okay, so these are the two modes of failure: pull out and rupture. Then we did some equilibrium analysis. From the equilibrium analysis, we tried to determine this friction angle. Okay, so if pull out governs, then increase in friction angle explains the increase in strength. And this increased friction angle, how to get this increased friction angle, we found it out here. Okay, at low confining pressures pull out failure happens, and at high confining pressures rupture happens. And what is and how much, so what, so this is qualitatively we are saying, right? At low, at high, what is the quantity, how much, from what value lesser than that we will have pull out failure, and from what value greater than that we will have rupture failure, that we can determine from this expression. Okay, then we solve one basic problem regarding this. So these problems I won't discuss anymore. Then we had testing of geosynthetics. Okay, so why do we actually need testing? Okay, why do we need testing of geosynthetics? To know their properties. Properties such as mainly strength, frictional properties, durability properties, all these things. For that purpose, we need to test all the geosynthetics before use. Okay, so what are some important standards? Some important standards for geosynthetic testings are given here. So for the geotextile, there are various properties that we need to find out. So some are physical properties, mechanical, hydraulic properties, endurance properties, and we have degradation properties. Degradation properties. So physical properties, what is the physical properties? Mass per unit area, thickness, stiffness, all these things. Okay. Then we have mechanical properties such as compressibility. Okay. See, you can see with applied stress, the thickness of the geotextile is going to reduce. Right. Mostly for woven type of geosynthetic, this happens. See, you can see for woven type of geosynthetic with applied stress, this thickness is reducing by a large amount. Then how to do the test, this superficial tier test. Okay, these tests we saw to find out the strength of the geosynthetics. We saw this video how. Then graph tensile strength. These two tests are actually very important. Trapezoidal test and this graph tensile strength test. Then we have punching strength test. All these videos we saw how in detail we saw how these tests are to be done. CPR puncture test, dynamic puncture test, seam strength test, all these tests. Okay. Then we had the hydraulic properties. So why are hydraulic properties important? We know hydraulic properties important because that helps us to design for filtration and for drainage, right? Okay, filtration and for drainage. So that's why hydraulic properties are important. So these hydraulic properties we studied. Then we have one very important property known as apparent opening size, with nothing but the 0.95 size, or sometimes 0.90 also. So we solve some problem regarding this. Then this is the expression to determine the cross plane permeability. So there are two types of permeability in geosynthetics, right? So one is the cross plane permeability, one is the in plane permeability. In plane permeability and cross plane permeability. So cross plane permeability determined by this, and in plane permeability some. One is transmissivity, and other one is, okay. So this one you can see this theta, this is in plane permeability. In the sky, it is all this gives this expression is for the cross plane permeability. Then we solve some problems. There are some more properties. So then we discuss geogrid testing, also quite similar to geotech testing. So this is this video we saw how to do. So we can do for one rib we can do the test, or for multiple ribs together we can do the test and find out for single rib. Okay, like this we can do some tests. So all these things we discuss. Then we discussed about the retaining wall. So why do we need retaining walls? We need retaining walls to support the soil laterally. Okay, so there are some various types of retaining walls, gravity, cantilever, and all those things. So we discussed the various types of retaining walls. So you can see here, yeah, you can see the various types. So these are the buttress retaining walls. Okay, sheet. This is actually a sheet pile wall. Okay, sheet pile wall. Anchored retaining wall, where some anchor is there. So these also we saw. Uh, so these anchored retaining walls are type of what? Reinforced retaining walls, right? So reinforced means what? Supported retaining walls. So what we are doing, we are actually supporting the retaining wall with some anchors, and then we can have these retaining walls or more different types where see here we are having modular blocks placed, and we are reinforcing the soil with some reinforcement layers. Okay, with the help of modular blocks. Okay, these are more different types possible. So in reinforced retaining wall, many types of arrangement are possible. One is full height panel wall, where this whole panel, this panel is a rigid structure. Then we can have segmental panel wall, where there are some segments. Okay, these segments are there. Uh, Not six segments. Separate segments are there, which are placed one by one to form the wall. And this is quite opposite to this one. So in the first full height panel wall, we have one single panel. In segmented panel wall, we have segments of panel. Then we have modular block faced wall. So there where we have some modular blocks that are placed one by one and then used to construct the reinforced wall. Then you have geotextile wraparound retaining wall. So without there is no facing. Directly we are wrapping the geotextile one by one about the soil, but there is no facing. So these generally we do not keep the reinforced soil wall like this. Reinforced soil walls are generally given some facing, because if we don't give any facing, there will be some risk, right? So someone may damage this geotext reinforcement, and that may be quite detrimental to failure, right? So that's why we always provide some facing. So main types of reinforcement: so geosynthetic reinforcement, we have geotextile, we have geogrid. Then steel reinforcement, we have steel strip, steel mesh. Okay, so these are the various wall configurations that we can have. So uniform reinforcement length, different reinforcement length, then back to back walls, all these are possible. So what are the main components of a reinforced wall? So we have the facing blocks. Okay, then the reinforcement, the reinforced soil, the backfill soil, leveling pad, and the foundation soil. Okay, so the facing blocks, leveling pad, reinforcement, reinforcing soil, backfill soil, and the foundation soil. So we saw this video where they showed how to construct a reinforced soil wall from start to the end. So why are leveling pads given? Leveling pads are actually made up of PCC, a plain concrete. They just give a plain surface for for us to construct the reinforced wall. Also, these are some important codes and design standards for reinforced soil retaining walls. Yes, so we discuss some of this. So what properties should the backfill soil have? Backfill soil should be granular, obviously. Okay, so high friction angle of the soil will result in high this friction resistance of the soil. So that's why you should have high friction. Low plasticity index, greater permeability. Why greater permeability? Because if the backfill soil has greater permeability, it will result in easy drainage of water. Okay, it won't uh, allow the water to accumulate, and if water accumulates, you know that there is going to be high hydraulic pressures. So we don't want that. So that's why that water should get drained out. So we want that soil should be granular and with high permeability, so that the water drains out easily. Then we just discuss on the lateral earth pressure theory. So all this we know: active earth pressure, passive earth pressure. These are the various load combinations. Then we solve some problems. Yeah, that's all. Okay, so this one is the fourth week. So in the fourth week, we we actually started design how design a reinforced soil wall. So to design a reinforced soil wall, there are some stabilities that we need to ensure. So what are the stability? One is the external stability and one is the internal stability. So for external stability, what are the main stability that we need to ensure? Those are the sliding stability, overturning stability, bearing capacity check, and the overall failure. Okay, to check for the lateral sliding, so we use this expression and then we determine the factor of safety. The factor of safety should be always greater than 1. So how did we get this factor of safety against sliding? So this factor of safety against sliding is given by resistance force by sliding force. So how, from where this resistance force comes? The resistance force actually comes from the frictional resistance developed at the base of this reinforced field. And the sliding force actually comes from the lateral earth pressure. Okay, the lateral earth pressure and this very horizontal barrier load. Okay, so all these we know which loads to take when, and from that we can determine the factor of safety. So this is the disturbing force and this is the resisting force here. So if you see here in resisting here resistance, we do not take the live loads. Okay, we do not consider the live the surcharge from the live loads. Then we saw this back-to-back walls. Okay, so back-to-back walls, how we need to uh, this check this this overlap length and all these things. We decided we saw this. Then after sliding check, we need to do overturning check. So in overturning check, we need to calculate all the overturning moments. So overturning moments are generated by the lateral pressures generated from the live load, the depth load, and the earth pressure of the soil of this soil. So all these things we calculated. Then we have the resisting moment. Right, we have the resisting moment. How to get the resisting moment? It's given here. Resisting moment will be due to what? So the overturning moment is due to the earth pressure, and the resisting moment is due to the weight of the soil, right? Okay, weight of the soil and this. See, you can see this resisting moment is from the weight of the soil, and the overturning moment is from the surcharge and the lateral earth pressure. So similarly, we need to calculate the factor of safety and we need to ensure that the factor of safety should be greater than 2. Then ultimately we need to check for the bearing capacity. Okay, we need to calculate the bearing pressure at the base of the retaining wall. Okay, we need to calculate the bearing capacity of the base of the retaining wall, and we need to ensure that this bearing capacity is actually greater than the bearing pressure. Okay, the bearing pressure that we calculate at this level. And you also need to ensure that the eccentricity is proper there, as because if the eccentricity is not in this range, then tensile forces will be generated at the base, and if you know that soil cannot take tension, right? So we need to ensure that the eccentricity of the vertical loads or the vertical pressure is in this range. And then we decided how to discussed how to determine the bearing capacity of this thing. Okay, so these are the seismic loads, how to calculate the seismic loads, everything from IS 1893. Okay, this we had discussed in brief. This is the seismic zonation map of India. How to calculate all the seismic loads we saw. Okay, so there are various methods with which you can actually calculate the lateral pressure. Okay, due to the seismic loads. So those are given actually here. So we discussed, and some problems were also given in the assignments. Okay, regarding this, and this is also important for exam point of view also. Okay, then this ends the external stability. Then we had the internal stability. So internal stability means there should not be any rupture of the reinforcement, and the reinforcement also should not fail in pull out. Okay, so we checked for this rupture pull out, and also one more failure that can happen, that is the connection failure. This means that this reinforcement is connected to the facing, right? So this joint, okay, this joint should not break. So if this joint breaks, if the connection between the reinforcement and the facing breaks, what will happen suddenly? Eh? excessive movement of the facing will happen. So this is holding it in place, right? So if it can just suddenly, there will be some excessive movement. Okay. So we discussed some of other internal forces that are acting. This is from this bridge abutment load and all these things. This also we discussed. Then how to calculate the horizontal force on each reinforcement layer, that is from this expression. Okay. Force transfer to reinforcement layer, same, this one. SV is the spacing, this is the vertical pressure, Kf is the what? This coefficient. Okay, so check for rupture. Force in reinforcement any depth should be less than the allowable tensile strength of the reinforcement. Okay, and if this is not true, then what will happen? The reinforcement is going to break. So you need to ensure that the force in reinforcement at any depth is always less than the allowable tensile strength of the reinforcement. How to get the allowable tensile strength? That ultimate tensile strength divided by the cumulative reduction factors. Okay, so here we are seeing force in reinforcement at any depth z. How to get this expression, right? So Kf is the earth pressure coefficient, Sv is the spacing, P is the vertical pressure. So how much embedment length we should have? So if this is the failure rupture plane, okay, rupture surface, then we should have at least 1 meter embedment length beyond that. And this was the rupture check. Then there was pull out check. So pull out resistance, we calculated the pull out resistance. How to calculate the pull out resistance? Twice of the vertical pressure into the uh, uh, length, this embedment length Le times the this friction angle, right? The friction ratio. So that is friction ratio alpha into 10 sigma. 10 pi r is nothing but the friction ratio times the vertical stress times the length. The factor of safety in pull out should be greater than 1. So we solved some, we designed uh, these things, right? In design, when we solve some problems, these things we discussed in detail. So as I was saying, this LTDS, this long-term reliable design strength, how to get this long-term reliable design strength, ultimate divided by or multiplied by different safety factors. And these are the various tests, connection test, strength test, all these things we saw. Pull out strength test. So then we solve some easy problems regarding this external stability, right? So external stability, we solved some problems regarding external stability. So we found out the earth pressure, all these things. Then we did the shear resistance. Then we find out the factor of safety in sliding. And similarly, we found out the water resistance. So we solved some easy problems. Okay. So this was it. Then in the fifth, so we began this fifth uh, lecture by solving some easy problems regarding this stability check. Okay, internal stability check, external internal stability check. So we solved some easy problems regarding this, and then what we did, we actually designed a geotextile wall. Okay, how to actually design a geotextile reinforced soil wall. So first we need to do what we need to do, determine the horizontal pressure as a function of depth. So total horizontal. So here the problems that we solved, that was taken from this designing with geocentrics book. So there they did not consider the seismic forces and everything. But in the class, the problems that were solved in the main classes, there this was considered. So in exam, questions might be there where the seismic force also we have to consider. Okay. So these questions just you can consider as a very basic, easy, this normal problem questions. So here you are seeing that they have not considered, but actually we have to consider the seismic force also. Okay, the force coming due to the seismic, this force might be coming due to the seismic load, that also we need to take into account. Okay, the horizontal stress, then we found out the spacing, we decided the spacing. Right, the load coming on each reinforcement should be less than the allowable tensile strength of the geosynthetic. From there we decided the spacing of the geosynthetic. Okay, then from by trial and error we decided a proper spacing. So then we decided that we place the geosynthetic like this in layers. After deciding the spacing, what we need to do, we need to determine the length. So there are two lengths, one is this length, other is the other length. One is the embedment length, and other is this LR length, LR, this LE. So how to determine this length LE? Determine this length LE, nothing from this, so nothing but from this expression. So actually this is nothing, but you can see 2 into C plus sigma Z tan delta, that is the friction resistance times the length, embedment length. Okay, we need to find out the embedment length, right? This embedment length Ng. So 2 times C plus sigma Z tan delta, that is nothing but sigma Z is nothing but the vertical stress time tan delta into 2 into Le should be equal to spacing times the horizontal pressure times factor of safety. So from there we get the expression for this embedment length. And what is this LR length? LR length we can directly get from, so we know this angle, right? So we are assuming that this failure rupture plane will occur at an angle of 45 plus 5 by 2, that is this active wedge, active soil wedge. So from there geometrically we can determine this LR length. So this is LR, so this is LE. So LE plus LR will give the total length of the reinforcement layer, right? Okay, then so then we decided how much length we should give. So LE, so here you can say LE is coming very less, but minimum embedment length, minimum this embedment length we have to provide as 1 meter. So minimum LE is provided, then LR we found out. So LR plus LE will give us the final length. Then we calculated the overlap length. So if you want to overlap the reinforcement, not seam them, so how much overlap length we should actually provide. Okay, so that was it, right? So this completed the internal, so this design actually satisfied the internal stability. Okay, and after that what you need to do, we need to check for the external stability. So now then what we did, we checked the external stability. Okay, which is the overturning stability and the sliding stability. Okay, similar to this, some more problems we solved. So that was it. Okay, so then in the, sorry, yeah, then in the sixth week we actually solved some problems regarding, first we started by solving some problems with geogrid reinforcement. So in the previous week we solved with geotextile reinforcement, then we solved with geogrid reinforcement. So geogrid reinforcement is the same concept only, external check for calculation for external. So here actually they have already designed for you, just you need to check for the stabilities. Okay, So we checked for all the stabilities and all those things, and then we checked for the internal stability. Okay, same to the previous thing. Then we came to embankment. Next we discuss the embankment. So when we called embankment and when we called a wall, so if any slope is steeper than 70°, it is designed as a wall, and anything lesser than that, slopes that are slower than that are designed as slopes. Okay. So we saw this how to check the stability for these embankments. Okay, how to so we actually need to the slip circle. So for completely cohesive soils, okay, cohesive soils, this wedge analysis is not required. Okay, directly this slip circle analysis we can do. But if the soil is a cohesive C5 soil, then what we need to do, we need to do this slip circle analysis with wedge. Okay, we need to divide the we need to first we need to assume a slip circle, then we need to divide it between certain number of wedges. I need to find out the factor of safety. Then we need to choose some other slip circle. So like this, we need to find out we need to use a search algorithm to determine the critical slip surface. Okay, and this slip circle, this factor of safety expression is given here, as you can see. So these are the resisting forces. This is the uh, this one. This is the resisting force, and this one is the sign component of the weight. The weight is the disturbing force. Weight of the wedge is the disturbing force, and this is the numerator. We have the restoring force or restoring moment. So restoring force, we also restoring force or restoring moment. You can see that TIYR. This is nothing but this is the moment that is generated due to the strength of the reinforcement that is placed. Okay, so this term actually comes from the reinforcement. So that will actually increase the factor of safety. So if reinforcement is not there, this term TIYY won't be present. But we place the reinforcement that will increase the factor of safety. Okay, so there are various methods to do this analysis. So that's what I discussed. Then we solve a easy basic problem to find out the factor of safety for a slope. Okay, then also we solve some problems where we use this Jewel's method to determine the factor of safety. Okay, to determine the factor of safety and also decide this length of reinforcement. Actually, where directly in Jewel's method actually gives the length of reinforcement. Okay, so that ensures that the factor of safety will be, see, the vector safety is to 1.4. That means the vector safety there, this will ensure that the design is safe. So this Jewel's method we actually used. This is actually the Jewel has actually given various charts. So directly you can use the chart to determine the length of reinforcement. So in the seventh week also we solved some problem with Jewel's method. Okay, so we plan to construct the soil embankment at 70° slope angle with horizontal and 10-meter height, reinforced with unidirectional geogrid, strength of geogrid is given, the soil properties are given, there is no pore pressure which is mentioned, uniform surcharge is given. We need to determine the number of spacing and the length of the individual geogrid layers. So what we use this graphs to actually determine all these things. Okay, these charts given by Jewel to calculate to solve the problem. So these problems are very easy and straightforward actually. Okay. So after that we started discussing our geocells. So why are geocell used? So geocells are used for reinforcement or embankment based soil. So say we have an embankment at the top Okay, at the base we have very soft soil. So to reinforce the not reinforce actually, is to support the embankment, we can place layer of geocell that will support the embankment over the soft soil. Okay. So there are many design principles that we can use to design with geocell. So one of the design is the by slip line method that was given by Jenner, Bush and Bassett. So that we discussed all these things we discussed actually, how to do from slip line method, how we can calculate everything. So I suggested that you read this read this research paper where everything is actually summarized very nicely. Okay, all other methods are also discussed how we can design with geocell. Okay, then we discuss this problem which was given in the class. Okay, how to actually determine from the slip line, with the hello slip line, how we can actually design with the geocell. Okay, then I discuss one extra topic regarding this unpaved road. Okay, so this is also related to sustainability. So what happened if you are to construct an unpaved road? Generally, if you do not use any geosynthetic, the thickness of the aggregates, okay, the thickness of the aggregates that you need to provide, that is actually quite high. So with the use of geotextile or geogrid, what we can do, we can reduce the thickness of the aggregate, so that that will what, that will aid in sustainability, right? So lesser material we need to use to construct the same length of the road. Okay, so so the depth of the aggregate layer we can reduce. How we can reduce? Just by placing a geotextile or geogrid layer. So we discussed all these things. I won't go into detail. So all these things we discussed, how to calculate, then we solved a problem. Okay, we solved a problem. So here you can see that without geogrid, we need to without any reinforcement, we have to provide a aggregate thickness of 0.31 meters. But if we use, okay, if we use a geotextile reinforcement, we can reduce that thickness by 50%. Right, we can reduce by more than 50%. We can reduce that. So that actually aids in huge saving. Okay, saving of cost. So all these things we have discussed regarding that. So first we discussed about geotextile, then we discussed about geogrid reinforcement. Okay, so in the eighth week we started by started our discussion on foundations. Okay, how to calculate the bearing capacity of foundations and all those things. What is bearing pressure? What is bearing capacity? Okay, all these things. All these things we cited. So what is shallow foundation? If the depth of the foundation is less than or equal to the ratio of the depth of the foundation to the width of the foundation is less than equal to 1, then we call the foundation as a shallow foundation. So what are shallow foundations? Examples: rafts, wall foundations, etc. And what is deep foundation? Deep foundations are nothing but piles and all, right? Piles and caissons, those are deep foundations. So pressure transfer to the soil should not exceed the safe bearing capacity. All these things we know. These are the modes of failure of the bearing capacity failure: central shear failure, local shear failure, touching shear failure. All these things we saw. Then how to actually increase the bearing capacity of the soil with by reinforcing it with geotextile or geogrid, that we saw. Okay, geotextile, geogrid or steel strips, that we saw. Okay, so we can use geocell mattress also to increase the reinforcement, the bearing capacity. So we can see that with unreinforced for the unreinforced soil, the there is rapid settlement. Okay, the bearing pressure, ultimate bearing pressure is quite less. But if we reinforce the soil, okay, with some geogrid or geocell or geocell whatever, we are seeing that the ultimate bearing pressure is actually increasing. So what are the most important points that we should be considered in this when we decide that we have to reinforce the soil to increase the bearing capacity? What are the main points that we should consider? The depth of first layer. Okay, the first layer of the reinforcement, where it should be placed, number of layers of reinforcement, length of reinforcement, the spacing of the layers of the reinforcement, the type of material of the reinforcement, and the shape and size of the footing that you are going to place. Okay. So what are the possible modes of failure? Okay, there are three modes of failure. One happens when the first layer is when the depth of the first layer is given by u and the width is b. So when the first layer is placed quite below, okay, u by b greater than 2 by 3, okay, okay, then the soil fails by bearing capacity failure of the upper layer. Okay, and when this u by b is less than 2 by 3 and the number of layers of are less than 2 or 3, then there is pull out failure of the reinforcement. And when the u by b is same, less than 2 by 3, but the number of reinforcements are higher, then there are chances that there is breakage, okay, the tear of the reinforcement. So these are the possible modes of failure that we discussed. Then these are some basic guidelines that we should follow for that. So we discussed all these things in detail, right? How to water this, where this shear is maximum, where the shear stress is actually maximum. In that point only, there is chances that this is going to uh, rupture. Okay, the reinforcement is going to rupture. So all these things we discussed. So theoretical analysis by Binkett and Lee, that we discussed how to calculate all the things. Okay, the Binkett and Lee have given everything. We just use their procedure to determine the depth and spacing and all these things of the reinforcement layers. Okay, everything is given in graphical form. So just let me go to the problem. Okay, so we have to design a strip foundation. So here we designed a strip footing and we chose the reinforcement layers that we need to, number of reinforcement layers, the spacing, all these things we decided. Okay, so we made this chart. All these things we actually did, so I'm not going to repeat. Okay, all these things we did. Finally, we decided the thickness of the reinforcement also. Spacing also we decided, thickness also we decided, all these things we decided. Okay, so this actually has to be solved by trial and error. Okay, this has to be solved by trial and error by changing the spacing of the reinforcement, by changing the first depth of the first layer of the reinforcement, by changing the number of the reinforcement. You need to find out the optimum arrangement. Okay. Okay, then in the ninth week we discussed about the PVDs, mostly PVDs. Okay, the vertical sand drains and PVDs. So all these things we discussed. So why are sand drains used? Sand drains are used to accelerate the consolidation process. Okay, so we solved a problem also where we saw that with the use of sand drains, the consolidation is accelerated. Okay, we solved some problems. All these things we discussed. How to calculate. Then we saw what are PVDs. These are nothing but prefabricated vertical drains. So where we have a core, and so the core is surrounded by a geotextile filter. The core actually helps in the drainage of water. So what happens? These sand drains and PVTs, they actually reduce the drainage path. Okay, reduce the drainage path, reduce the drainage path by providing more drainage options. And with this, what happens? The consolidation of the soil is accelerated. So after the soil, we consolidate the soil. What we can do? We can construct the whatever we want to construct over that land, over that soil. We can do that. Okay, so there are some advantages and disadvantages of both sand drains and PVTs. Those were discussed. So these are the arrangement of PVTs that we follow: square arrangement or triangular arrangement. All these things we discussed. Then we solved some problems also. Okay. Then one more thing we discussed was vacuum consolidation. Okay, what is vacuum consolidation? So generally, what we need to do, say we have PVDs given, right? PVDs given. So what we need to, provide some pressure. Okay, we need to increase the vertical pressure over the soil to give some overburden pressure, so that the effective stress increases. And with the effective when the effective stress increases, the pore water pressure is going to get reduced by drainage. Okay, as soon as we increase the so in order for the drainage to take place, we need to induce some change in increase in effective stress in the soil, right? So for that, what we do, we generally provide some preloading, okay, with some surcharge. So that can be actually substituted by using vacuum pressure. Okay, that can be substituted by applying vacuum pressure. So this topic we discuss. So what is the benefit of applying vacuum pressure? What happens at all the depths? At all the depths, we have a uniform increase in effective stress. Okay, at all the depths, there will be equal and same increment of effective stress. But what happens? So say, but contradictory to that, if we want to increase the effective stress with the help of, say, preloading with surcharge, okay, by applying some load over the soil, what will happen? At the top portion, the increase in effective stress will be higher, then it will reduce as the depth increases, right? The increase in effective stress won't be actually uniform. But if we use this method, okay, this vacuum consolidation method, so we can achieve faster pre-consolidation. Why? Because over all the depths we can have a uniform increase in effective stress. Okay, how this actually happens, we also discussed it here in this portion. We saw how this is actually happening. Okay, this was that. Then we discussed the stone columns. So what are stone columns? They actually stone columns are what? Aggregate columns that were actually constructed, that so with the help of its rigidity, it actually supports the increases the uh, strength of the soil. Okay, so these are the various modes of failure that also we discussed. And one more thing is the encased stone column, where in the stone column we encase with some geosynthetic material. The advantages we discussed, the effect of the what is the effect of confinement that we discussed. How to estimate the load carrying capacity of a stone column, that is given by IS 15284. This we discussed in detail, and we also solved some problems regarding. So step by step, everything is given in the IS code. It's very easy if you go through it. Directly everything is given. The steps we need to follow and find out the load carrying capacity of a stone column. We solve some problem regarding that also. Okay. Okay. So then in the 10th week we discussed about the filtration and drainage. Okay, the filtration and drainage, and we solved a number of problems regarding filtration and drainage. Even in yesterday's class also we solved a problem regarding leachate drainage also. So we solved many easy and simple problems regarding this filtration and drainage. So what is filtration? Filtration means to stop soil to pass, to provide a barrier to soil, but to allow water to pass through it. Okay. Okay, so it should act as a sieve, right? So it should stop soil to, it should not allow soil to pass through it, but it should allow water to pass through it. So that is what filtration is. So what is the purpose of filtration? Filtration actually prevents piping of the soil, the loss of soil particles, and it helps the easy passage of water through it. So this all this filtration we discussed. What is filtration? There are many criteria that we can follow to design filters. So one is the retention criteria, other is the permeability criteria. So this retention and permeability criteria, many codes have given many criteria that we can follow. So it is up to the designer to choose. Okay, so we discussed all these things. You can see all these things we discussed in detail. Then there is a test called gradient ratio test. This gradient ratio test is done to establish the compatibility between any geotextile and the soil, whether it can be used, whether that geotextile can be used with that particular soil to act as a filter. Okay, to establish that compatibility, we do this gradient ratio test. Okay, then we solve some easy problems regarding this. Okay, so in filtration, the thing that govern is the cross plane permeability. Okay, that is given by permittivity, and drainage is governed by in plane permeability. That we'll see. So permittivity, this actually determines the cross plane flow of water. So how to determine the factor of safety? All these things we saw. Already solved many problems we solved. So I am not going to repeat this again. Then we have drainage. So drainage, this in-plane flow of water. So we provide geotextile, okay, geotextile or geonet or geocomposite, so allow water to easily drain out, okay, drain out from the soil. You can see here this theta is nothing but the transmissivity. This is determined for any geosynthetic. It is determined using the concentrate test. And we solved some basic problems regarding drainage also. We saw how to determine the factor of safety and all these things. All right. Okay. Then on the 11th week we discussed on this erosion control. Okay, the erosion control. What type of structures or geosynthetics we use to actually prevent erosion in different cases. Okay, riprapes, concrete linings, pre-connecting, these gabions, then this geotextile, then geocells, many things we studied. Okay, then we saw that why this natural geosynthetics made up of this jute fiber or coir is actually important in because of sustainability reasons. Okay, this we saw. Then we solved one problem regarding this erosion control where this riprap is there when we have placed a geotextile below it. Okay, which acts as a filter. Okay, this geotextile acts as a filter, and this geotextile will actually prevent the loss of this beach sand from here. Okay, that we saw, and the factor of safety also we determined. Okay, so all these problems we solved, and yesterday class, as you know, we discussed on these landfills. Right, so landfills, water landfills. Okay, why are landfills actually required? Water engineered, non-engineered landfills. Then, what are the types of waste? Municipal solid waste or hazardous waste. So based on that, we need to decide the liner system. What are liner system? Single liner system, double liner system. All these things we discussed. Right, single liner system, double liner system. Where we are to use which one. So all these things we discussed. And then we discuss the properties of geomembranes. Okay, so geomembranes are what? Geomembranes are one of the most important liner materials. Okay, along with compacted clay, these geomembranes are used. So these properties of geomembranes are some properties of geomembranes are very important. So one important property is water vapor transmission that we discussed. Then we saw that this how to determine this thickness. Okay, this thickness, how to determine the thickness? You can seeing that it's directly dependent on the allowable stress. Okay, this allowable stress you need to determine from tests. This allowable stress on any geomembrane, this has to be determined from test. So we saw what is water vapor transmission test, how to do this water vapor transmission test, how to do the calculation from water vapor transmission, how we can get the permeance and the Fickian this permeability or diffusion. And this permeability is not Russian permeability. This permeability is Fickian diffusion, right? So this permeability can be converted to Russian permeability by just manipulating, playing with the units. So we did that one also too. So you change the units and converted this to Larsen permeability or hydraulic conductivity. And this problem is solved regarding this drainage, okay, drainage of leachate. Then we saw this geometric consideration, how to calculate the depth, okay, average height, average depth of the reservoir. These things we saw. Then this thickness, how to get the thickness. So what happens is that, say you have placed a geomembrane. So what will happen? So due to the vertical stress, sometimes there might be some settlement in the there will be some settlement in the geomembrane. So what happens whenever there is this settlement? Due to this settlement, there are some tensile stresses that get generated in the geomembrane. Okay, some tensile stresses are generated that get generated in the geomembrane. So these tensile stresses should be actually uh, the geomembrane should not tear up due to these tensile stresses. So how can we, so we need to choose a thickness so as that this, whenever there is excessive settlement, this uh, this tensile stress just develop just actually doesn't tear up the geomembrane. So we need to choose the thickness in such a way. So how to choose that, how to find that out? So what we did, we just equated it in the horizon x direction. We just equated all the forces. So in x direction we have this p cos beta. This is the horizontal component of the tensile this stress, that is equated with the, that will be balanced with the shear resistances that develop. Shear resistances on the top of the layer, at the bottom of the layer, this top layer, bottom of the layer. Okay, these two, all this we saw. And this top shearing resistance will be zero if there is water over the geomembrane, or if there is very thin covered soil. Okay, then it will be zero. So all these things actually solved yesterday. We won't go again. Then we saw the step how to determine the factor of safety of a slope where a geomembrane is provided. Okay, that we saw for infinite slopes, finite slopes with uniform cover, and then with tapered cover. All these things we saw. I gave you all the formula and how to calculate. Then at last we saw this run out and anchored trench. Okay, how much run out length should be provided, and if you are providing an anchored trench, what should be the depth of anchored trench, that we saw how to calculate all these things. Then also we saw that we can actually make a design chart for ourselves. Okay, by varying the T allowable this run out length and the depth of the trench, we can vary this and you can actually prepare a design chart. Okay, so that was it. So uh, yeah, so with this actually we will end today's session, this discussion session. Just it was just, I just went very fast because in 1 hour I had to do, so I just did it very fast from beginning to the end. How to actually it's whatever what we actually studied in all these 12 weeks from first to the end. So first we so initially first we just introduce the topic, right? First we just a so the first was just the introduction. right? The first was just the introduction. Then we discussed about the reinforced soil, what were the mechanisms of reinforced soil. Then we discussed this reinforced soil walls, how to design reinforced soil walls, how to choose the spacing of reinforced soil walls, how to decide the length of reinforcement, all these things. Then we studied the external stability, how to the sliding stability, wire turning stability, all these things, the internal stability checks, right? All these things we saw. Then for slopes, okay, for slopes we found out the factor of safety. We saw how you can calculate the factor of safety for reinforced and unreinforced slopes. Okay, then we saw this geocell, how we can use the geocell below an embankment, that we saw, right? All these things we saw. Then we saw accelerated consolidation with the help of PVDs, how PVDs actually help in accelerated consolidation, how to design them, all these things we saw. Then stone columns we saw, how to determine the load capacity using the ice code, how this ice code, how we can calculate the load carrying capacity, all these things we saw. Then erosion control, okay, this erosion control we saw, drainage, filtration, all these things with this, so that how we can design this, how to calculate the factor of safety. And at the end we saw for liners actually, okay, for liners how can we design, calculate for geomembrane, some geomembrane properties we saw, what are the different types of liners, properties of geomembranes, how to determine the thickness of geomembrane, how to uh, calculate the runout length, how to determine the depth of cut range, all these things we so, okay. So with this we will actually end today's session. So if you have any doubt, you can ask. I hope everything was clear. Okay.
Hello.
Yeah, yeah, yeah.
Yeah. Sir,
Uh, uh.
actually, what is infinite slope, sir?
Infinite slopes means very big slopes. Okay, very large slopes. Say fine. Simple example can be a hill slope. Okay, very large hill slope. That is actually considered as an infinite slope. But a normal say you are constructing an embankment. Okay, short
Yes.
embankment, that is a finite slope. Okay, infinite slope means very large, huge. These hills, natural hill. You see, na, that is spread over,
Yeah, yeah,
yeah, very large, huge hills, mountains that are infinite slopes. Mountainous slopes are actually infinite slopes. But if we consider, talk about this here, the embankment slopes, those are really embankment are say 10-meter high, okay, say 50-meter, 150-meter width, that much is the limitation, right? So that those are actually considered as is finite slopes. Okay, so based on that actually the this mechanics of the problem actually changes, whether you consider a problem as a infinite slope or whether you consider a problem as a finite slope. All right, so generally for embankment and all these things we consider, when embankments and dams and all these things we consider finite slopes only. Okay.
then, sir,
Okay.
factor of safety of the embankment slope.
Yeah,
During
yeah.
the continuous rain,
Uh, uh,
during the continuous rain, how do we calculate the factor of safety of the embankment?
during continuous, so I think for continuous rain, this infiltration and all you have to consider. Okay, the pressure, water pressure, that is, so see, actual mechanics is very different. When there will be rain, the soil gets wet. What happens after that? There will be some pore water pressure that is getting generated in the soil. So all these things actually can be generated. In that case, what happens? The strength of the soil reduces, right? So what will happen? The soil becomes wet. Soil becomes wet, the pore water pressure in the soil increases. If the pore water pressure increases, the effective strength of the soil, effective stress increases. If the effective stress increases, the strength of the soil will obviously increase, because if you recall from the basic soil mechanics, the mode column, this it is given by C plus sigma. This sigma reduces, then what will happen? The strength of the soil will also reduce. Right, so all these things actually, see, manually we cannot do things, but if you go into very like say these complex software such as this geoslopes, the many softwares are there actually, geoslopes and all these things, they actually consider, okay, this infiltration pressure, what will be the pore water pressure that gets generated due to infiltration of rainwater, all these things you can actually simulate. Okay, due to using finite element method, finite difference method, okay, even with the limit equilibrium method in geoslope software, all these things actually can be simulated. Manually it is very difficult to do. Okay, using this softwares, na softwares, we can do this complicated calculations. What will happen, how the pore water pressure changes when rainwater is actually flowing, and all these things actually we can do, because these are dynamic problems, right? These are so as rain falls, the continuously the pore water pressure is changing, the soil gets wetted, there is loss of strength of soil. So all these things actually we need to simulate proper. Just we cannot simplify these things, right? There are many
Right, sir.
so there are many codes, there are many things that have given some factor of safety that you can consider and all these things, but they also have reached to that point by doing many analysis. So generally what happens is that whenever we design, okay, whenever we tend to design, say we want to use the we want to stabilize a slope, we are seeing that every year due to rainfall a slope is failing. Okay, so what we need to do, we need to say, we decided we need want to reinforce the slope with soil nails or whatever. So what we do, we generally use some numerical tools. Okay, we use some numerical tools, finite element software, some such as abacus or say Lexis. It is console, many softwares are available, commercial softwares are available. So they are using this finite element method, limited to finite difference method. So what we do, we can simulate all these things. Okay, how much, due to the rain, how much pore water pressure is going to continuously increase. So as rain falls, the amount of water accumulated, all these things, this actually is very like what to say, uh, we need to go more in depth. Okay, then this unsaturated, this soil also come into unsaturated soil mechanics also come into play. Generally what we need to do in basic soil mechanics, we decide, we whenever we solve the problem, we solve in such a way that the soil is completely saturated. So rain will come, soil will be saturated. But actually, what happens? Soil might not be completely saturated. So unsaturated, this unset, okay, unsaturated soil mechanics come into play. All these things. So these are, we need to actually model this with the help of certain complex software. So these softwares, commercial packages are have actually included all these concepts. Okay, with the help of that, we can design them.
Now, another question, sir.
Yeah.
In the slope, embankment slope,
Yeah.
it's enough embankment.
Uh,
But if any uniform loading on the top, that
uh,
we are designing.
Surcharge,
That is
surcharge.
the top that we can design.
Uh,
But the same way, the uniform loading in the slope.
uh.
How do we calculate that one?
Uniform loading
Uniform load in the slope of the embankment.
means on the
Any
slope.
loading in the slope.
On the
Yeah, in the slope.
on the
Yeah, on the slope.
on the slope, I don't think uniform. Generally, see on the generally here we are discussing about embankments only, right? So at the top, say we are constructing
Yes,
an embankment. At the top, we are constructing a road. Okay, due to that, the
yes.
loading on the road, that we are converting it to UDL. But on the slope, I am not sure how we can do that, because say we are having say we have a, so see, for small slopes, that is for small slopes in the means I am not sure actually what you are asking. So in the slope you are asking that how to provide the loading, right?
Yes.
But why do you want to put loading on the slope?
In the some that department are like that boulders, no sir.
Acha
That
for
boulders, yeah, like that boulders. Yeah.
okay, that I am not sure actually. Maybe we can convert it to some point load or something like that. I'm not sure. Okay, I have to see that.
Yes.
I'm not sure about this.
Okay.
Okay.
That and sir, can I contact you any doubt, sir?
Yeah. You
Through
can.
mail,
Yeah, you can
yes,
contact.
your
I will.
mail and the phone number.
Yeah, I will.
Mail and the phone number.
I will give you. Just a second.
Sir,
Okay, I have given the phone number, mobile number, WhatsApp number, and email. Okay,
not
in the chat.
thought. seen, sir.
Not visible.
Good. Yeah, not visible.
Just
Not
a second.
visible.
Just a second. Huh? Now is it visible?
Not visible, sir.
I I
Okay, sir. 78
s-
738
it's 72969 and email ID also I have.
72969 72969 and the mail at a very very small letter. It is very
Okay,
small.
okay.
Thank you,
Just a sec.
thank you.
Just a second. Uh,
Yeah.
uh,
Okay, okay.
uh,
Thanks.
uh.
Yes. 20 at 8 dot in.
Okay,
I
okay,
know.
na.
I will send the query, sir.
I
Kindly answer me.
yeah, sure, sure. Okay. You can mail, okay. You can mail and it mail, okay. You can mail or you can what you
I
send in
will mail, sir. I will
WhatsApp also. No problem.
mail. Okay, okay. You can.
Okay. Okay. Thank you.
Thank you very much. Thank you very much.
Thank you. Have a good day.